In the heart of our universe lies a realm where the rules of classical physics cease to apply. This is a place where the very fabric of reality behaves in ways that defy our everyday experiences and challenge our understanding of the natural world. This is the quantum realm, a strange and wonderful place where particles can exist in multiple states at once, defying the binary nature of classical physics. Here, particles can be in a state of both here and there simultaneously, a phenomenon known as superposition. In this realm, particles can communicate instantaneously across vast distances, a mysterious process called quantum entanglement. When particles become entangled, the state of one particle is instantly connected to the state of another, no matter how far apart they are. This means that a change in one particle will instantaneously affect the other, a concept that Einstein famously referred to as spooky action at a distance. It is a world that has captivated scientists and philosophers for over a century, ever since the early 20th century when pioneers like Max Planck, Albert Einstein, and Niels Bohr began to uncover the strange behaviors of quantum particles. Their groundbreaking work laid the foundation for what we now understand as quantum mechanics, a field that continues to evolve and expand our understanding of the universe. This quantum realm is not just a theoretical curiosity, it is the foundation upon which the revolutionary field of quantum computing is built. Quantum computing leverages the unique properties of quantum particles to process information in ways that classical computers cannot. By harnessing the power of superposition and entanglement, quantum computers have the potential to solve complex problems that are currently beyond the reach of even the most powerful classical supercomputers. Quantum computing harnesses the bizarre yet fascinating laws of quantum mechanics to perform calculations in ways that were previously unimaginable. Traditional computers use bits, which can be either a 0 or a 1, to process information. However, quantum computers use quantum bits or qubits, which can exist in a state of both 0 and 1 simultaneously, thanks to the principle of superposition. Unlike classical computers, which rely on bits to represent information as zeros or ones, quantum computers employ qubits. These qubits can exist in a superposition, meaning they can be in a state of both 0 and 1 simultaneously. This allows quantum computers to process a vast amount of information at once, making them incredibly powerful for certain types of calculations. These qubits can exist in a superposition, meaning they can be in a state of both 0 and 1 simultaneously. This ability to be in multiple states at once is what gives quantum computers their immense power and potential. But that's not all. Quantum computers also leverage another quantum phenomenon known as entanglement. This fundamental difference is what gives quantum computers their immense power and potential. When qubits become entangled, the state of one qubit becomes dependent on the state of another, no matter the distance between them. This interconnectedness allows quantum computers to perform complex calculations at unprecedented speeds, solving problems that would take classical computers millions of years to crack. In the following sections, we will embark on an exciting journey into the heart of quantum computing, exploring the principles and technologies that make it possible. We will delve into the fascinating concepts of superposition, entanglement, and quantum interference, and see how they come together to create a new paradigm of computing, exploring three key concepts that underpin its power: superposition, entanglement, and quantum interference. These concepts are not just theoretical. They have practical applications that are already beginning to transform industries, from cryptography to pharmaceuticals. So fasten your seatbelts and get ready to have your mind blown as we delve into the fascinating world of quantum computing. This journey will not only expand your understanding of the universe, but also open your eyes to the incredible possibilities that lie ahead in the quantum age. Imagine a coin spinning in the air, neither heads nor tails, but existing in a state of both possibilities at once. This is not just a trick of the eye or a clever illusion, it's a glimpse into the fascinating world of quantum mechanics. In this realm, the rules of classical physics no longer apply. Instead, we encounter phenomena that defy our everyday experiences. One such phenomenon is superposition, where particles can exist in multiple states simultaneously. Superposition is a fundamental principle of quantum mechanics that sets it apart from the classical world. It allows particles like electrons or photons to be in a combination of states until they are observed or measured. In the classical world, objects have definite positions and velocities, but in the quantum world, particles exist in a cloud of probabilities, only taking on definite properties when measured. This means that an electron can be in multiple places at once, or a photon can take multiple paths simultaneously. This is famously illustrated by Schrödinger's cat, a thought experiment where a cat in a box can be both alive and dead until observed. When we measure these particles, they collapse into a single state, a process known as wave function collapse. This collapse is what gives us the definite outcomes we observe in experiments. Understanding superposition is crucial for grasping the power of quantum computing. Unlike classical computers that use bits as the smallest unit of information, quantum computers use qubits. Classical bits are binary, confined to a single value of 0 or 1. This binary nature limits the computational power of classical computers. Quantum bits or qubits, however, can leverage superposition to exist in a combination of both states at the same time. This means a qubit can be both 0 and 1 simultaneously, vastly increasing the computational possibilities. A single qubit can perform operations on both 0 and 1 concurrently, effectively processing more information than a classical bit. When we combine qubits, the power of quantum computing grows exponentially. 2 qubits can be in 4 states, 0, 0, 0, 1, 1, 0 and 1, 1 simultaneously, allowing for parallel processing on an unprecedented scale. This ability to explore multiple possibilities at once allows quantum computers to tackle problems that are intractable for even the most powerful classical computers. They can simulate complex molecules, break modern encryption, and design novel materials with ease. Imagine a world where we can simulate the behavior of complex molecules to discover new drugs, or break encryption codes that are currently unbreakable, or design materials with properties we can only dream of today. This is the promise of quantum computing, a technology that goes beyond the binary limitations of classical computing and opens up a universe of possibilities. As we continue to explore and develop this technology, we stand on the brink of a new era, an era where the boundaries of what is possible are constantly being pushed and redefined. The future of quantum computing is not just about faster computers, it's about transforming our understanding of the universe and our place within it. Researchers around the world are working tirelessly to unlock the full potential of quantum computing. Their efforts are paving the way for breakthroughs that could revolutionize industries from pharmaceuticals to cybersecurity to materials science. Quantum algorithms are being developed to solve problems that were once thought unsolvable. These algorithms take advantage of the unique properties of qubits, such as superposition and entanglement, to perform calculations at speeds unimaginable with classical computers. Entanglement, another key principle of quantum mechanics, allows particles to be interconnected in such a way that the state of one particle instantly influences the state of another, no matter the distance between them. This phenomenon is being harnessed to create ultra-secure communication networks and powerful quantum sensors. Imagine a world where data can be transmitted securely over vast distances without the risk of interception. Quantum networks could make this a reality, providing unprecedented levels of security for our digital communications. Quantum sensors are also poised to revolutionize fields like medical imaging and environmental monitoring. These sensors can detect minute changes in physical quantities such as gravitational waves or magnetic fields with incredible precision. The journey into the quantum realm is just beginning, and the possibilities are endless. As we continue to push the boundaries of what is possible, we are not just building better computers, we are unlocking new ways to understand and interact with the world around us. The future is quantum, and it promises to be a thrilling adventure beyond the binary. Visualizing a qubit in superposition can be tricky. The concept of superposition is fundamental to quantum mechanics, yet it defies our classical intuition. In classical computing, a bit is either a 0 or a 1. However, in the quantum realm, a qubit can be in a state that is a combination of both 0 and 1 simultaneously. This is what we call superposition. Enter the Bloch sphere, a handy tool that helps us represent the state of a qubit in a three-dimensional space. The Bloch sphere is a geometrical representation that allows us to visualize the complex state of a qubit in a more intuitive way. By mapping the qubit's state onto a sphere, we can better understand its properties and behavior. Imagine a sphere with a north and south pole. The north pole represents the classical state of 0, while the south pole represents 1. These poles are analogous to the binary states in classical computing, but the Bloch sphere allows for a continuum of states between these poles. The north pole represents the classical state of 0, while the south pole represents 1. But unlike classical bits, Qubits can exist in a superposition of these states, represented by any point on the surface of the sphere. This means that a qubit can be in a state that is part 0 and part 1 at the same time. Now here's where it gets interesting. A qubit in superposition doesn't reside at either pole but can be any point on the sphere's surface. This surface represents all possible states a qubit can be in, with the poles being just two of the infinite possibilities. A qubit in superposition doesn't reside at either pole but can be any point on the sphere's surface. The position on the surface is determined by two angles, theta and phi. Theta represents the latitude while phi represents the longitude. These angles help us understand the probability and phase of the qubit's state. The qubit's latitude on the sphere represents the probability of it collapsing to 0 or 1 upon measurement. If the qubit is closer to the North Pole, it has a higher probability of collapsing to 0. Conversely, if it is closer to the South Pole, it has a higher probability of collapsing to 1. The equator represents an equal probability of collapsing to either state. A qubit located at the equator has an equal chance of collapsing to either state. This is a perfect example of a qubit in a balanced superposition, where it is equally likely to be measured as 0 or 1. This balanced state is crucial for many quantum algorithms that rely on superposition to perform complex calculations. The longitude of the qubit on the Bloch sphere represents its relative phase, a more complex concept related to the wave-like nature of quantum particles. The phase is crucial for understanding quantum interference, where the relative phase between qubits can lead to constructive or destructive interference, affecting the outcome of quantum computations. This phase information is crucial for quantum algorithms and interference effects, which we'll explore later. Quantum algorithms leverage the principles of superposition and interference to solve problems more efficiently than classical algorithms. Understanding the phase and probability of qubits is essential for designing and implementing these algorithms. The Bloch sphere provides a powerful visual tool for understanding and manipulating qubits, enabling us to visualize their state and the effects of quantum operations. By using the Bloch sphere, we can gain insights into the behavior of qubits, design better quantum algorithms, and ultimately harness the power of quantum computing to solve complex problems that are beyond the reach of classical computers. Prepare to enter the realm of spooky action at a distance, as Albert Einstein famously dubbed it. Entanglement is one of the most mind-boggling phenomena in quantum mechanics, where two or more particles become interconnected in such a way that their fates are intertwined, regardless of the distance separating them. Imagine two entangled particles like tiny spinning coins. Measuring one particle and finding it to be heads instantly determines the state of the other particle as tails, even if they are light years apart. This instantaneous correlation defies classical intuition and highlights the deeply interconnected nature of the quantum world. Entanglement plays a crucial role in quantum computing by allowing qubits to be linked together, forming powerful computational resources. By manipulating one entangled qubit, we can instantly affect the state of its partner, enabling complex computations and algorithms.